Good morning. I'm Spot On Weather Meteorologist Matthew Euler, and today we're going to continue our training on mid-latitude systems, areas of low pressure, areas of high pressure. This is the second part of the training on mid-latitude systems. These are the systems that frequently move across the United States and impact our weather. So if you've ever been curious as to the dynamics or how high pressure systems form or how low pressure systems form, what causes that explosive development or intensification of existing lows, bomb cyclogenesis, low development off the east coast of the United States in wintertime, you're in the right place for the training. So let's get right into today's training, and I'm going to kick it off with the favorable area for cyclogenesis in a long wave trough. Now, cyclogenesis, as I mentioned in yesterday's training, part 1 training on mid-latitude systems, cyclogenesis refers to the development of an area of low pressure or a storm system and or the intensification of an existing area of low pressure or storm system. And when we look at the jet stream maps, the jet stream charts, which are typically looked at the 300 millibar level in the atmosphere, which is at about 30,000 feet above the ground where we live, we're looking for specific favorable areas on that jet stream map. Now, in the jet stream map, you have what's known as long waves. They're relatively stable waves, and they're very large amplitude waves. That's generally the axis of the jet stream. If you look at the blue shaded area here on the graphic, this is the common formation area, which is typically downstream of the trough axis. If you look at the black dashed line, that's the trough, the long wave trough axis. And conditions are very favorable just to the east of this long wave or downstream of that long wave trough axis. So if I'm looking at a jet stream chart or the model data for jet stream level winds or positioning, I'm looking for these kind of favorable locations just downstream of the trough axis for areas of low pressure to develop or storms to develop. Development of a Baroclinic Low. Now, a couple major points as we move into the new section on development of Baroclinic lows. Intense cyclogenesis normally occurs at and just downstream of a negatively tilted diffluent trough. Now, I'm going to show you an example of what this looks like, so just bear with me here. We did kind of briefly mention about downstream of the trough axis, which is generally in the northern hemisphere. It's going to be positioned to the east of that long wave trough axis where that jet stream dips down at the furthest lowest point. That's the trough axis. So we do kind of understand downstream is basically following the winds. It's basically downstream, downwind of those winds. So I'm going to break it down here. We'll talk about negatively and positively tilted troughs, and we'll talk about this diffluent trough as well. Now, negatively tilted troughs, if I were to basically describe what it looks like, negatively tilted troughs are oriented from a northwest to southeast axis. So they basically extend northwest to the southeast. Negatively tilted troughs are normally associated with enhanced diffluence or divergence or removal of mass aloft, and thermal advection, enhanced thermal advection. So when we get these negatively tilted troughs, we generally have a very, very large temperature gradient and very strong cold air moving into an area, very strong warm air out ahead of the low pressure moving northward in that same area. Here is what a negatively tilted diffluent trough would look like on an actual weather chart. There's an upper level low that's positioned over Iowa in this particular graphic. And you notice the solid black line, that is your negatively tilted trough. So you see how it extends basically from northwest towards the southeast, the axis of this negatively tilted trough. And then diffluent basically means that your height contours, the solid black lines that run across this chart, those height contours are spreading apart. And as they spread apart, they remove mass in what's known as diffluence. Okay, so now weak cyclogenesis, so you usually have weaker storm systems that occur at and just downstream of a positively tilted confluent trough. Right, and I'll show you what the positively tilted trough looks like here in a minute. Now, positively tilted troughs are oriented more northeast to southwest. In a lot of cases in the atmosphere, we get, the majority of the cases are more positively tilted troughs. And for a trough to be considered confluent, the contour, the height gradient, the contour gradient, the height lines must increase downstream of the trough axis. Let me show you what this looks like. In a lot of cases in the atmosphere, we have positively tilted troughs. Some of the major, more memorable storms, especially in the wintertime, East Coast winter storms, are associated with a negatively tilted diffluent trough. But in most cases, the upper level troughs are tilted in a positive manner from the northeast towards the southwest. So see that black solid line coming out of the upper low, that's generally running from northeast to the southwest direction, okay, the orientation of the line. And then confluence indicates the solid black lines are generally to the east of that trough axis are increasing, and they're also coming together, getting closer together. And that would be an example of confluence where the air aloft is accumulating, the mass is accumulating aloft, and that is not very favorable for explosive storm development. Now, the jet stream pattern associated with any kind of storm development, the cyclogenesis, is typically occurs under diffluent flow aloft is where you're going to find those storms developing in association with the jet stream. The jet stream pattern plays a huge and significant role in the development of low pressure systems and storms. This diffluence is many times indicative of divergence in the upper troposphere. So basically, again, you have that removal of mass aloft, and as air aloft is removed, you have to have another location in the atmosphere where that mass is replaced, and that comes from below. And so you get this low-level converging air where the air is coming together, meeting, and then rising vertically in the atmosphere to help replace that divergence or diffluence, the mass removal aloft. Now, upper-level troughs are often deepen when the wind speeds upstream of the trough axis are greater than those downstream. Stronger equatorward or southward directed winds on the backside of the trough often enhance the cold air advection into the trough axis, thereby amplifying the trough. Now I'm going to show you, I believe I have a map here. I'm going to show you that here in a minute. The determination can be made based on contour spacing across the trough axis, and we'll evaluate the overall change in contour spacing across that trough axis. So bottom line here, to summarize that second bullet here on the slide, when you have an upper level trough, so that's an area of lower height in the upper atmosphere, when you have the upper level trough, it's going to get more amplified or deepen when you have stronger wind speeds basically coming into the trough, digging that trough deeper. Okay, let me show you what it looks like here. So in this example, I'm showing you a 300 millibar chart. So this is up at 30,000 feet in the atmosphere. Now, the very dark solid lines indicate where the jet stream is located. That's the outer edges or the boundaries of the jet stream. So generally those solid, really black, dark lines are the outline of the jet stream. The arrows show spacing of the height contours. So you see the arrows with the solid dark line with arrowheads on both sides. That indicates the spacing of the height contours, which are the lighter colored black solid lines. Okay? All right, so we have a trough axis. That's the point at which this trough is the deepest. It looks like in this particular image, it's located over the Colorado-Utah border, extending down and southward all the way down into Mexico at this point. Do you notice one thing here? See how big the arrow is on the right? See how large that line is with arrowheads? That's indicating diffluence, or spreading apart of height contours, and that is going to be a favorable location for the storm to develop, for cyclogenesis to occur, because you're having more mass removed aloft that is being replaced from below. If you have more mass removed over the top of a developing storm, the storm will deepen, the vertical air motion will increase. If you look at the far left part of the graphic with the arrow, with the solid dark line and the double arrowhead, you'll notice the height contours are much closer together. And that is indicative of more of a confluence, where those height contours are getting closer together. They're packed over a tighter spacing. We still have a lot of wind in that case, but that's indicative of confluence aloft or the addition of mass over the top. And we don't want the addition of mass over the top in the upper atmosphere because that will result in sinking air motion, will help to favor the development of high pressure, surface high pressures or anticyclones. Right, so we have these long waves which are fairly stable and they generally occur at 300 millibars or 30,000 feet in the atmosphere, and they're associated with the jet stream. We also have what's known as short waves, which are much more unstable, and these short waves play a significant role in the development of low pressure systems and storms in general. Now, short waves with baroclinic lows to the surface, they are supported by these upper level shortwave troughs. So again, the atmosphere is a three-dimensional feature to where you have a surface area of low pressure storm system producing all that kind of precipitation at the surface with probably a lot of wind if it's a fairly intense cyclone. But that stacks back. It stacks back aloft to the mid levels of the atmosphere where these shortwave troughs are located. And recall from the part one of my training yesterday that baroclinic instability, that's going to transfer energy from those stronger westerly winds up at the jet stream level and accompanying temperature gradient. You know, we get a very strong temperature difference. You might drive 50 miles and see like a 10 to 20 degree temperature drop in the wintertime with some of these very strong systems. So you get this temperature gradient along with very strong jet stream winds aloft. And the baroclinic instability transfers energy from those higher level jet stream winds and then also taps into the temperature gradient. And that basically creates takes potential energy of position, and converts it into kinetic energy or energy of motion. And that all of a sudden you get motion, you get wind, you get mixing of air masses, and the storm eventually deepens if we have the right upper level shortwave trough support as well as the upper level jet stream support. Generally, if there's no major shortwave up at about 500 millibars or 18,000 feet, then there will be no significant surface storm development or cyclogenesis. Without a major shortwave, there will be a lack of. So these are some of the ingredients we look for when we look at the weather charts. You know, a jet streak. If there's no jet streak, or what we sometimes call a jet max, which is an accelerated area of winds within the jet stream itself. Divergence aloft, we want that removal of mass aloft. Baroclinic instability, again, that taps into the thermal or temperature gradient plus the energy transfer down from the jet stream level from those winds towards Earth's surface. A stable wave may be supported by a minor shortwave trough, but it will be unable to intensify further. So in this case, when I say stable wave, I'm talking about a fairly weak storm system. Now, the low-level structure, baroclinic lows are going to derive their energy from baroclinic instability. Again, that's those higher wind speeds in the westerlies along with that stronger temperature or thermal gradient. The strongest temperature gradient occurs along the polar front, which typically occurs around 60 degrees north latitude average position. In order for a low to remain baroclinic, it must be supported by the polar front jet. That's what the PFJ stands for, the polar front jet stream. Okay. Now, Pedersen, I mentioned him yesterday briefly in part one, but Pedersen's rule is so significant in the field of meteorology, and he came up with this rule that cyclogenesis, the development of area of low pressure or the intensification of a low pressure, will occur when and where there's an area of upper level divergence, which is often indicated ahead of the shortwave troughs by positive vorticity advection, that's PVA, once it's become superimposed over a low-level frontal zone with weak thermal advection. So a lot of cases what Pedersen's rule is applying to is having a stationary frontal boundary, and you have a weak, really the winds are blowing pretty much parallel in opposite directions. So we really don't have any mixing of the air masses just yet. North of the stationary front, we have cooler air. South of the stationary front, we have warmer air. And so you get this cyclogenesis, this development of a storm system or intensification of an existing stable wave or weak low pressure. When you have that upper level divergence, again, we have to have that upper level support. And again, it's often indicated by what's known as positive vorticity advection. We have higher values of vorticity at 500 millibars at 18,000 feet blowing in over this low-level frontal zone, we get the development of a low pressure, and things can take off from there. Simply put, cyclogenesis will occur when a shortwave trough moves over a weak frontal boundary, but you need the upper level support to really get a storm kicked off and to intensify. This statement does not mean that positive vorticity advection must reside directly above the surface front. Often that PVA is superimposed over the frontal zone, but somewhat poleward, which means to the north, or further west toward lower thickness values. So we don't have to have that upper level shortwave trough and the positive vorticity advection out ahead of it directly over that surface front. So here's a graphic kind of showing you all these ingredients and how they come together for surface cyclogenesis to occur and how it interacts with that shortwave at 500 millibars or 18,000 feet. So we have an area of surface low pressure on this thickness chart with a cold front extending southwestward from it. There is a warm front extending to the east of the low pressure system. We have these yellowish, orangish lines, solid lines encircling your area of low pressure, and those are indicating your isobars on this particular image. So you notice the isobar immediately surrounding this low pressure system, which is represented by that black L, that's 1,004 millibars. And there's another isobar, a line of equal barometric pressure, further outward away from the low pressure, which is at 1,008 millibars. That's represented by the 0.8. Then we have these dashed lines, which represent the thickness values in the atmosphere, ranging from 552 to 564 decameter thickness. And then the purple shading indicates the positive vorticity advection, PVA, as it starts to interact, override, coming in at 18,000 feet aloft over the top of this area, weak area of low pressure. And so all the ingredients are there. You'll notice that the positive vorticity advection, the purple shading, is actually not completely over the entire length of the frontal systems, but pushed back to the poleward, northward, or to the lower or colder thickness values. Lower thickness values, colder temperatures. Now, Pedersen's rule brings together all the mechanisms causing cyclogenesis. We have the jet stream support, and that would be in the form of what's known as a jet max or a jet streak, where we have favorable upper level divergent quadrants of the jet stream or jet max aloft over our location. We have a major shortwave trough moving in at 500 millibars or 18,000 feet with this area of positive vorticity advection, that PVA, moving in over the low pressure system. And then we got the thermal field where we got a strong temperature gradient or thermal gradient. And they all must interact for rapid cyclogenesis or rapid storm development to occur. And this does happen. This happens quite frequently along the east coast of the United States in winter when we have very large thermal field, a very large thermal gradient between the warmer Gulf Stream and the much colder land areas off the east coast of the United States. We get very strong jet streams that move through with the jet maxes, the jet streaks, and we definitely have shortwave troughs that can pivot and move through the long wave trough. So we definitely see this happen. If any one of these features is missing, then we'll most likely would have a weak surface low, and the development would be rather slow and short-lived. Now, application of Pedersen's rule, there's only going to be a few short waves which cause development of strong baroclinic lows. So you may have minor short waves which only show up at one level in the atmosphere, and these may interact with a low-level frontal zone and perhaps a weak area of low pressure kicks off. But in general, there's a lot of these upper-level troughs that move through the pattern. But there's only a few of these that are major short waves that can actually really develop baroclinic lows. Now, a low may not form at all when the shortwave trough is well behind the cold front. So position means everything. Timing of the features, all these features have to come together at the right time. You have divergence ahead of a shortwave trough. If that occurs behind the surface cold front in the region of that colder air, that's not going to do the low pressure any good, and basically that low will not intensify. The storm will not get stronger. Because you get pressure rises with cold air that are going to offset the pressure falls associated with the divergence aloft. So we have equal and opposite things happening back in the colder air behind the cold front. Here's an example of a shortwave trough with the positive vorticity advection, that PVA in the purple shading, well removed and away from your low pressure, well removed away from your surface front. And it's back in the coldest air with the lowest thickness values. The colder air, it's going to want to resist vertical motion and cause sinking air motion because it's more dense. And then you get, upper level divergence with the PVA, the positive vorticity advection, ahead of the shortwave trough, but they're just basically going to act equal and opposite to each other, and you're really not going to get anything to explosively develop in this case. Now, shortwave troughs, moving over cold and often dry air masses, you can get divergence or removal of mass aloft ahead of the shortwave trough, but if it occurs over that cold air mass again, well behind the surface front, we're really not going to get any explosive storm development. Cyclone development at the surface cannot occur because there's no local increase in the thickness values. And we want an increase in thickness. We will need some warmer air getting injected into the system, which is going to result in increases in thickness, a more expansive atmosphere, and that's just not going to happen in this case. Now, divergence aloft, the removal of mass aloft, is going to promote low-level convergence, where the air comes together at the surface, and cyclogenesis, the development of a storm at lower levels. However, that cyclogenesis often does not occur here because of offsetting effects in that colder surface air. And again, we're talking about colder air moving in, cold advection. That's going to decrease your thickness values in the atmosphere, and it's going to oppose cyclogenesis. Colder air is heavier. It wants to sink. The atmosphere becomes more compact. So instead of rising thicknesses, we have shrinking or lowering thickness values, which opposes the development of storm systems. A lifting of stable dry air, that will allow for rapid adiabatic cooling. So as your air rises, there's going to be a cooling aspect to it, an expansion, and most likely you'll get some cloud development. That adiabatic cooling, though, is going to result also in a local decrease or drop off in the thickness values, and that again is a factor that will oppose cyclogenesis or the development of a storm system. Lifting an air mass that is this stable requires too much energy. So you got to think about the atmosphere. Think about if you're ever at the gym and you have a 50-pound dumbbell and you have a 25-pound dumbbell. Okay, when you try to lift that 50-pound dumbbell, the heavier one, that is going to require much more energy as compared to that 25-pound dumbbell. So as a result, the atmosphere works very similar manner in that if the atmosphere has to try to lift stable, colder air, all that energy is going to be utilized into just trying to do that. This atmosphere is just not going to have much energy left over to utilize to actually form a storm in cyclogenesis. So not only is the adiabatic process a braking mechanism here, but it's actually strong enough to stop the cyclogenesis process before it starts. So this is a case where you might be looking at the models, and you look at them and we're 5 days out, and you see this massive storm system trying to develop, and it's getting stronger, it intensifies, it deepens, and 2 days later on the models, that storm system is completely different, has a different look, it's completely weak. It's because the air may have been too cold and stable, cold and dry, which offsets what you really want. It offsets the divergence aloft. Here's an example again of how we have a shortwave trough moving in, the purple shading, indicative of positive vorticity advection, PVA. It occurs well removed from the frontal system, the frontal boundary, well removed back in the coldest air, and this just simply is not going to, there's a weak surface low in this case, but it's just simply not going to be very strong. Dynamics just aren't perfectly aligned in this case. Now often only a surface trough will form the coldest air beneath the divergence aloft. You won't really get a full-blown storm system to develop or area of low pressure. Instead you get that surface trough, but rarely do you get that cyclone or that low pressure to develop within the cold air away from the surface front. However, if that cold surface air mass is shallow and the front displays only a gradual tilt with height, you could get some cyclogenesis along the slope frontal zone at levels above the surface. So you get what's known as extensive overrunning in that case, overrunning precipitation, which is often well observed behind the surface cold front in these situations. So Sometimes, with most cases with cold frontal passages, you get high pressure to build in right behind those frontal passages. The winds are from the north, the northwest in the northern hemisphere, and you get more of a cooler, drying out process. But in this case, if you have a sloped, you have a cold surface air mass that's shallow, the front only displays a gradual tilt or slope with height, you may actually get overrunning. And whenever air rises or overruns colder air, it tends to saturate, form clouds, and possibly precipitation. Intensification of a storm system is going to really require that divergence and thermal advection to amplify the upper level shortwave. We talked about baroclinic instability yesterday and how a shortwave gets amplified over time based on an out of phase relationship where your height contours, your lines of equal temperature, isotherms, are not perfectly aligned with each other. They're not lined up with each other. And you get crossing of your isotherms across your height contours, and that's going to result in temperature advection. But you also need that divergence. You're up at the jet stream level at 300 millibars or 30,000 feet. You're going to want that upper level divergence or removal of mass over this developing storm. And you also need that strong temperature advection. Most commonly occurs along a slow-moving cold front is where you get these conditions, where you have the temperature gradient will supply energy for development of the storm as that cold air advection, CAA, causes a 500 millibar trough to deepen. And you get cyclonic winds to start blowing or turning around that area of low pressure. And that is associated with some vorticity or some spin in the atmosphere. And that's going to favor easier development of the storm system, of the Baroclinic Low. Upper level conditions most favorable for intensification of a shortwave trough. So we talk about shortwave troughs. Again, a trough is simply an area of lower heights in the atmosphere. Shortwave troughs typically occur at 500 millibars, 18,000 feet above the ground, as well as 700 millibars, 10,000 feet above the ground. So when I say shortwave troughs, we're talking about areas of lower height aloft at 10,000 to 18,000 feet. You get strong surface cyclogenesis and is associated with a rapidly intensifying shortwave under a divergent upper flow, usually displaying a large amount of diffluence. Diffluent upper flow is common in a negatively tilted trough. So why are negatively tilted troughs so much more intense as far as storm development goes? We have we have stronger storms with negatively tilted troughs, and it's basically right there. You have a greater amount of diffluent upper flow, and that is basically going to result in mass being removed aloft much quicker than that can be replaced from below in the lower atmosphere. So you have some very strong rising vertical air motion as a result. Now the shortwave trough intensifies as it moves into the long wave trough position. This is known as wave phasing, which produces overall greater wave amplitude. So these shortwave troughs are superimposed over the longer wave troughs at the jet stream level at 300 millibars or 30,000 feet. Here's an example of developing baroclinic low. This is where we look at all the ingredients in one particular slide. The image on the left shows an area of low pressure with frontal boundaries, a cold front southwest extending southwest, a warm front to the east. If you look back behind it, you have some dashed lines, some thickness values. But aloft, above the image on the left, above that low pressure on the left, we have an area of, it looks to me like we have an area of positive vorticity. Now in this case, the image on the left, it's showing the positive vorticity situated a little bit further back. But in general, we have this major shortwave trough aloft that's going to support the development of that surface low. And then over time, look at the image on the right, it shows the amplification of that shortwave trough. And see how it gets deeper, how it digs deeper aloft. That X represents the highest value of vorticity. That's known as a vorticity maximum on the chart. And then you have a surface low pressure beneath that is explosively developed now. So that's really what happens in this case. So the development of baroclinic low, there's something that's known as self-development. It's basically a feedback mechanism that once one step starts, it continually feeds into other steps and the storm system gets stronger and stronger. Now self-development is, here's some ingredients for it. We have this divergence aloft or removal of mass aloft, which is often indicated by what's known as positive vorticity advection, that PVA, ahead of your major shortwave trough, it's superimposed near the baroclinic surface low. And then that divergence or removal of mass contributes to cyclogenesis. Cyclonic circulation then strengthens as a result. The cyclonic circulation or spin gets stronger, and then the temperature advection occurs around that low pressure. Stronger warm air advection then builds your major shortwave ridge out ahead of the major shortwave trough, and then you get stronger cold air advection, deepening the major shortwave trough. So we get amplification of the wave and the mid-levels of the atmosphere. We get building upper level features such as height gradients, wave amplitudes, the jet intensity. We have an area of very strong blowing winds aloft, as well as vorticity. The rate of spin is increasing the vorticity advection. And that vorticity minimum occurs typically in ridges, and that eventually becomes smaller. The vorticity maximum value in the trough becomes larger. So now we have a larger vorticity gradient in the mid-levels of the atmosphere, and that's also favorable for continued development and progression of the low as it develops. So divergence ahead of the shortwave trough will strengthen. Divergence between the trough and the ridge is stronger. Divergence causes that surface low to deepen or get stronger, and further cyclogenesis or intensification occurs. And this is called the self-development because once development starts, it continues until some other influence acts to offset or stop it. And those influences that eventually act to stop or offset it are known as braking mechanisms, which we'll get into that a little bit later. They basically are safety checks in the atmosphere. A cyclone can only reach a certain maximum peak intensity, and then it's going to eventually run into these braking mechanisms, which we will cover. All right, so this is the self-development of a low. This is a really great graphic. Let's see how we got here. This puts everything together right here. This is a great graphic, and this shows you the vertical air motions are represented by the solid blue and the solid red arrows. So you notice that the air sinks, the arrow's pointing down from aloft. From higher in the atmosphere, it's pointing down, that blue arrow, towards high pressure at the surface. So we have sinking air motion generally above a surface anticyclone or high. And then with the red L, the area of low pressure, your storm system, we have a red arrow pointing up, and that indicates rising air motion. Notice where that rising air motion in storm development occurs. It's going to occur downstream or just to the east of the long wave trough axis. And we have sinking air motion behind that trough axis. Notice that the low-level thermal gradient is there as well. We have the pink color represents warm air advection, where air temperatures are increasing, warmer air is moving into colder areas, and then the blue area in between the high and the low, the H and the L, that blue shading indicates cold air advection, where you have basically lower thickness values as well. So this is how everything plays into the development of a low pressure, the self-development of a low. We have thermal gradient via warm and cold air advection. We have vorticity advection occurring in the mid-levels of the atmosphere. You'll notice the pink shading. That pink shading above the low pressure indicates the positive vorticity advection area. The blue shading indicates negative vorticity advection, or lowering of the vorticity values. And again, that shows you the vertical air motions associated with each in general. And then also remember, local increases in the thicknesses near the cyclone promote cyclogenesis. As discussed in a physics section, the hypsometric equation specifies that thickness is a function of the mean layer virtual temperature. So in general, warm air advection or increasing temperatures will raise the virtual temperature. Moisture advection is also going to raise the virtual temperature. We're bringing moist air into the area. And then local diabatic heating. When I talk about diabatic, remember it's heating or cooling from below, and moistening of the air. And latent heat, they generally raise the virtual temperature. Right now we move into braking mechanisms, and that's basically going to be the end of my training today on part 2. As I mentioned, cyclones can only reach a peak intensity. There is eventually going to be what's known as a breaking point for cyclones. And thankfully, we have what's known as braking mechanisms to basically offset, slow down, or eventually stop the further development of a baroclinic low. All right. Self-development is going to initiate these braking mechanisms. As that low deepens or intensifies, gets stronger, the braking mechanisms begin opposing further development. And I'm going to show you some examples of some of these braking mechanisms soon. These braking mechanisms will eventually offset the self-development process. Here are some of the types of braking mechanisms I'm talking about. We have boundary layer processes. Remember, the planetary boundary layer occurs from the surface to 3,000 feet above the ground. And within this surface to 3,000 foot layer, you have wind that blows across the surface, and as the wind blows across the surface, it's going to have friction. Friction is going to act and be an issue as the winds get stronger. As they blow stronger around this area of low pressure, the storm system, those winds increase in speed, the pressure gradient gets much more steep, and friction is going to act to slow the wind speeds down. It's going to act to accumulate mass. So friction, that's going to enhance your low-level convergence where the airstreams meet. And it's also going to partially offset the removal of mass aloft because you're adding mass at the bottom of your column when you have a lot of friction. So that boundary layer process is very important, friction. Also, pressure falls in that low pressure center produce an increase in what's known as the isobaric gradient or isobaric wind, which enhances surface convergence. Just keep this in mind, the isobaric wind is an ageostrophic wind produced by pressure rises or falls as cyclones or anticyclones weaken or intensify. Ageostrophic refers to when the forces are out of balance. So here's an example of boundary layer convergence and friction. Friction is basically going to cause cross isobar flow in toward the low pressure center because as the winds blow across the Earth's surface, they're going to get slowed and perhaps change direction based on friction. Adiabatic processes are another braking mechanism for lows. Vertical motion increases as the low strengthens, so we get stronger upward vertical motion. Adiabatic processes and stability will help determine the strengthening. So, for example, with adiabatic lifting, the adiabatic process with lifting is a cooling process which locally reduces the thickness values and thus stifles or impedes cyclogenesis. The cyclone braking mechanism inherent in the lifting process can be reduced if the lifted air is only slightly stable. So if you have warmer, moist air lifted as opposed to cold, dry air, you can overcome this braking mechanism with adiabatic processes. The lifted air quickly reaches its level or lifted condensation level where the base of the cloud forms. This promotes condensation and latent heat release. And this also implies an abundant moisture source for the developing cyclone. So we want cloud bases or lifted condensation levels, LCLs, closer to the ground because moisture is more abundant in the lower troposphere in that case, which implies a greater amount of latent heat release during the process of condensation. So while both braking mechanisms, we talked about boundary layer convergence and due to friction, as well as adiabatic processes, while both braking mechanisms are at work throughout the life cycle of a baroclinic low, they dominate at different times. For example, the adiabatic process is more dominant during the stable and unstable wave phases, and the boundary layer convergence is more dominant during the mature and decaying phases. So bottom line, adiabatic processes play a larger role in the beginning stages of the storm development, whereas boundary layer convergence is towards the latter stages of development. All right, that wraps things up. We just got through with braking mechanisms. Today we talked about the self-development of a low-pressure system. Generally, what happens, this is a great graphic again to show you of the fact the atmosphere works in a three-dimensional capacity. Even though we live here at the Earth's surface and we might get rain and feel the actual effects of the dynamic processes behind the low pressures, or maybe we get that nice blue sky when we have high pressure move in. There's a lot of up and down vertical motion that's occurring even above us here at the ground in association with these two different pressure systems. We have warm air advection, cold air advection, and there's also these shortwave troughs and shortwave ridges up at 18,000 feet in the atmosphere that can enhance or possibly weaken storms depending on where we're located in relation to those. So I hope you enjoyed this training today. I really enjoy this material on the atmosphere And I plan hopefully to cut part 3 here within the next couple days. And that should wrap things up on this particular training topic. Very interesting. This is the meat and potatoes of meteorology right here. All right, that wraps things up today on the training, spot on weather. If we're not spot on, we're not doing it right. Have a great day, everybody. Take care.